namely, but first of all, there's this delta from our A drum to A drum, completed interval A drum. Defined as follows. Well, we just go. Oh, sorry. Right, so there are some obvious definitions and theorems, except here now, remember this was this F completed power series algebra. And this is just defined by taking AI to AI tensor 1 plus 1 tensor AI. We just define it so that these will be the primitive elements. And then you get a map of this sort. So if you want to do this formally, of course, what we would use is the fact that this is a completed free algebra. So we can sense this anywhere we want at the finite level and take inverse limits. So that's the idea. So there's something of this sort. And then using this, we get this map from A drum sub x for the sheaf to A drum sub x completed tensor product, this kind of thing. And then the theorem, whose proof is all formal at this stage, is that, one more definition first. So from our category of unipotent bundleless connection, we have this Durand fiber functor now, which takes us to vector spaces over F, which just takes a bundleless connection and sends it to the fiber of V at X. The same as before. Right. And now, I think I used X before, but I'll use by A Durand nabla 1, where 1 is inside the base point, the fiber at B, with some fixed base point B. Then the theorem is that the Homs from FB to Fx is isomorphic to A Durand sub x, and the tensor compatible isomorphism from the fiber functor at B to the fiber functor at X is isomorphic for something I'll write as P Durand of X. By definition, consists of the elements in A Durand of X such that delta of A is A tensor A, and again the augmentation is 1. Now, let me make a comment about this. This is true for any smooth variety X, even a compact one. If you just look at it for affine case, first of all, it looks kind of strange because I identified all the fibers with A anyways, right? But for a projective variety, a compact variety, there won't be a canonical identification of all the fibers. But nevertheless, I gave that illustration to make it concrete. And for a for a projective variety, you have to describe this somewhat differently. But I gave it that description for some concreteness anyway. But this theorem still holds in the same form, just with a slightly different definition of A Durand and everything. So that's one remark. And as I said, the proof just follows from the universal property of the bundle stated earlier, which still holds even in the projective case with a slightly twisted definition. So let me give one example, in fact. If you did this over C, if F equals C, so that you started with a variety over C, and then, so you have your point B, and suppose you actually had a topological path gamma from B to X. Right? Then this gamma actually defines a point in P duram of X. So why? This is, and maybe in fact, maybe I'll call it P duram of gamma, just to distinguish it from the actual path. Meaning, this is by parallel transport. This is in the sense of differential geometry, really. You know? So if you have a bundle with flat connection, or a bundle with any connection, in fact, then and any path, then there's a canonical, given any bundle with connection, you know, then there's a map from the fiber at B to fiber at X, yeah, determined by any path. Then simply take any vector here, yeah, and choose the parallel section which takes that value, and take the value of the parallel section over here. You have to do it patch by patch, of course, and go over many times. But eventually there's this well-defined parallel transport of vectors from one fiber to another. But then, according to our theorem, this can be expressed as an element inside this A duram X, right? Yeah. And what is that element? That element really is simply, assuming, again, we trace it back to the affine case where I described everything. So that element, if we take algebraic differential form, will be exactly, so P duram of gamma in this case will be summation of words, yeah? And what is this? I'll write this as the integral from B to X of alpha sub W. Where alpha sub W is literally now an iterated integral. Namely, so, yeah, oh, sorry, yeah, I should have said it in this way. Sorry, this is slightly misleading notation. This is not incorrect, but let me rewrite this. Right. So, what is this element? Oh, actually, no, sorry. What I wrote is correct. Sorry. So let me rewrite this. P duram of gamma is summation integral from B to X of alpha sub W, where this is an iterated integral, where if you have a word AI1 through AIM, yeah, then by this, I mean the iterated integral of alpha I1 through alpha IM. In the previously defined sense, you integrate this, view it as a function, multiply onto the next thing, integrate that, view it as a function, multiply onto the next thing, and keep going in this manner. Yeah. So this way you really get an iterated integral this way. And so if you believe the previous theorem, of course it includes the fact that an element of this or is group-like. And that assertion incorporates a lot of these identities that we're discussing, these shuffle identities that were discussed in virtual lectures and so on, are simply contained inside the statement that this is a group-like element. Okay. Now let's go back to the arithmetic case. Now f over qp will be a local field. And we have, here's the setting. X is a smooth variety over spec f, which sits inside a smooth scheme over spec OF. And I'll denote by y the special fiber. And we'll assume that this whole thing has a good compactification. So everything smooth in that picture. And x prime minus x is an étal divisor. Oh, sorry, I guess here I'm implicitly assuming I'm on a curve. I may as well do that. So let me assume now that everything is a curve. These are all curves. I take this to be an étal divisor. You don't need to do that quite yet, but I may as well do it since that's the main case of interest. Then further notation is this. If we take an f point of x prime, this is the compact thing. Remember, these are the compactification. Then you have maps from here to y prime of little k. So here, of course, little k, I'm denoting little k, the residue field. This is the specialization map, where we take the closure into an OF integral point and then reduce mod m. So this is the specialization from f points of x to k points, x prime to y, k points of y prime. And if we take a k point of y prime, which denote by y with these brackets around it, the inverse image on the specialization of y. So the map, the point in x prime that reduce to y. This is sometimes called the tube of y. That's the basic notation. And the thing is, this setting determines another fiber functor. So if we have now y inside y of k, we get another y fiber functor, which I'll write fy sub y the crystalline fiber functor that goes from the unipotent bundle with connection on x. This is the U drum from a moment ago. So again, vector space is over f, and this is defined as follows. We take a bundle with connection and send it, I'll write it in this way, to the horizontal sections over the tube of y. This is V bracket y, the tube of y, then the nabla equals 0, that's the way it's written. So what does this mean? Well, this is a locally free sheaf on x, but then we can view it, look at analytic sections of this thing on the tube. So these are the analytic sections over OX. Yeah, so this algebraic functions tensored with these are the convergent analytic functions, convergent power series, which makes sense. I'm assuming everything is smooth here, so we can choose a little coordinate at y. Yeah, that makes sense of what it means to be convergent power series using any coordinate. And this notion is independent of the coordinate because any two coordinates will be shared by some invertible element. So we take convergent power series, and then this thing here refers to horizontal sections in that thing. This. So in other words, solution to the previously discussed equation in convergent power series around y. Yeah. And the fact is that these always exist. There are plenty of such solutions. So the theorem is that this, actually maybe I'll give this a name. Maybe I'll write V analytic y for this bundle just over this locally free module over the analytic functions on y. So V analytic y has a basis of horizontal sections. That is, this thing here is just the horizontal sections cancelled with y. So it's generated by horizontal sections. And the proof is easy if you consider the classification theorem that I stated a moment ago. Yeah? So what's the idea? Is that, remember, we can assume that V looks like Ox to the n together with the connection D minus summation alpha I and I. So remember this classification theorem, yeah? Where these alpha I, they algebraic differential forms, right? And definitely, so these guys themselves can be written in terms of a coordinate as a convergent power series here on this disk. So that's one fact. So it will be algebraic restriction of an algebraic function on some affine open neighborhood. Now, if you consider the differential equation, so we can assume this. Then each of these alpha i's in some coordinate will be some fi of z dz, where these are convergent. Okay. And antiderivative will therefore be convergent. On open unit disk. Yeah, that if you take the convergent power series of this form, restriction of an algebraic function on some neighborhood, then antiderivatives are all convergent. So in fact, this is the completely elementary argument. So I won't give the details there, but you just use that classification. So what we actually get, there's even more. And I don't understand the analytic issue well, so I won't emphasize it too much because I've been just citing other people's theorems. But near the compactification devices, these solutions are even over-convergent. Disk of radius strictly less than 1 around the compactification point, where these things will still be convergent. Where do I want to move here? Okay, maybe I'll just try it here. Right. So what we get eventually is the following diagram, in fact. Suppose you take 2 point x prime inside the tube around y. So remember y, little y here, is a rational point of the special fiber. Then you have Vx, the fiber of any v given v at x on the one hand, and fiber of v at some x prime. But then we have the horizontal sections on the tube, on the whole tube. And then what we just discussed is that the maps to the fibers are all isomorphisms. Because these are generated by the horizontal sections. So what we get is an isomorphism from here to here, which maybe I'll call P Chris from x to x prime. Between any 2 points on in a given tube, you get a canonical isomorphism this way. And this, of course, is parallel transport again. And this makes perfect sense in this region, on this tube. Because what do? We take any vector here and find the horizontal section with that value at the fiber at x, right? And they take the value of that horizontal section at x prime. And that's the isomorphism from here to here. So this is parallel transport literally. And the same as the differential geometric setting, as long as we stay on this tube. Now there are some other tricky business associated to this parallel transport, and so it's where I'm going to have to go a little bit even more quickly. So let's phi going from y to y. will be the Frobenius map. And by Frobenius here, I mean the K-linear Frobenius. This is some finite field. You don't have to, you can even define the absolute Frobenius, but I'm not going to bother. Just take the power of the absolute Frobenius, that's K-linear. Yeah? Take the K-linear Frobenius. Yeah. And what we can do is we can use this business to define the Frobenius pullback of a bundle with connection. Yeah? We can define this. This is an aspect of the fact that this category of unipotent bundles with connection on X is actually equivalent to the category of overconvergent isocrystals on Y. It actually only depends on Y. Yeah? But in a sense, this discussion is a part of the proof of this fact. So we need to prove all these things. But, and so here, because I don't understand rigid analytic geometry very well, I'm still a little bit sketchy on the detail. There's a paper by Kara-Lotto and Lustum that carries this all out in very carefully, following an outline by the Lin. But here's the idea. So how does one define this kind of thing? I mean, part of it is very old machinery. It's this idea of Grothendieck, that if you take a morphism on the special fiber, then any two lifts of the same morphisms are homotopic in some sense. So more precisely, yes, so you define this using local Frobenius lifts. But if you want to do this, then of course, given two different lifts, you have to be able to identify them somehow. You know? And the idea is this. Suppose phi 1 tilde and phi 2 tilde are two Frobenius lifts, which may occur on the overlap of two local lifts. Two lifts of phi 1 for phi. Then you consider the lift, the pullback by this one of some given V nabla, and then pullback by the other lift of the same bundle with connection, and compare the two. And the thing is, then there exists a canonical isomorphism between any two lifts. So this is the Grothendieck's homotopy business that I was referring to just now. You know? And by the way, so this is easy. The only tricky part in general is that suppose that these were actually integral flat bundles with connection, meaning they live on all of the model X. If suppose they were actually bundles with connection on the whole model, then actually it's easy to construct this thing. But the only difficulty here is that these only actually live on the generic fiber, so that some convergence issues come up. If they lived on the whole integral model, then the categories are even just, this category of bundle with connection is just the category of crystals, integral crystals. So you don't have to worry, all these discussion becomes much easier. But let me just give you the idea of what happens here, is this. Suppose you look at this fiber by fiber, instead of looking at the shifts here, they call it. Then the fiber at X, at some given X, so what is it? So the fiber will be, the fiber of V nabla at phi 1 of X, right? And same for this phi 1 tilde of X. And the fiber of phi 2 here at some given X will be V nabla at phi 2 tilde of X, right? But we said a moment ago that, see, since these are lifts of the same point, yeah, they lie inside the same tube. Yeah? So the specialization of phi 1 tilde of X is simply phi of the specialization of X. Yeah? So these two, this is the same as the specialization of phi 2 tilde of X. So in fact, there's a canonical isomorphism between these two things using flat sections. So this uses the connection, of course. This wouldn't be true. You wouldn't have such a thing. Of course, you would have such an isomorphism, but the point is that using the connection, you have a canonical isomorphism between these two lifts. Yeah? And this all patched together. So this patches together give shift theoretic isomorphisms. So there's a canonical thing of this sort. So you choose local Frobenius lifts and define local pullbacks, but then on overlaps, any two local pullbacks, there's a canonical isomorphism between the two, so you get descent data. And so, but by the way, this isomorphism is analytic. But then you get an analytic bundle at the end, and in the projective case, by Gaga, that this gives you an algebraic bundle. That's the idea. In the non-projective case, you have to work a little bit harder. First, you have to consider a log connection under compactification. First, you prove that any unipotent bundle has logarithmic singularities. And then you examine what this means on some blow up of the fiber, of the diagonal divisor inside the product of the two varieties. But let me also say just a little bit more formally about what the shift theoretic version of this statement is. Right? As I said, the full technical details is one of these crystalline things that go on and on. But I'll just say a little bit more about this. So more formally, what we're saying is this. So X has a diagonal embedding into X cross X, right? And inside here, it actually will denote by delta sub 1, the rigid analytic neighborhood, analytic tube of radius 1 around the diagonal delta. So that's what's going on. It is, what we have here is this. If we have phi 1, two lifts, phi 1 tilde and phi 2 tilde, then in fact what we get is a map from X to this neighborhood delta sub 1 inside X cross X. The map from X to X cross X actually factors through this neighborhood of radius 1 because they're lifts of the same thing. So if you think about fiber by fiber, it will always be contained inside the tube of radius 1 around the diagonal, the product of the two things. Phi 1 tilde and phi 2 tilde actually lands inside here. But in fact, if we look at the connection, now this thing, there's a projection to X, projection 1 and projection 2. And the point is that projection 1 pullback of the connection is canonically isomorphic to the projection 2 pullback of the connection on this rigid analytic neighborhood. That's what this convergence condition is, the existence of these convergent sections. If you look at it, not point by point, but if you look at it actually globally, shift theoretically, what it means is that on this whole thing, the two projections are isomorphic. This is Grundig's interpretation of a connection anyways. A connection refers to this isomorphism from one projection to another on infinitesimal neighborhoods. And the convergence thing. So normally the formal connection is where you do this on the formal completion. A connection itself is simply on the first order infinitesimal neighborhood. That's what the usual connection is. The formal connection is just, the integrable connection is just on this whole formal completion. A convergent connection is exactly one of these things. And the theorem is that the unipotent connections are all convergent. That's actually what underlies this thing. So in fact, what we can do is we can take this map to pull back this guy. So the official definition, when you've done this all correctly, of this Frobenius pullback, now returning to this panel, is just that projection pullback. That phi 1 tilde cross phi 2 tilde pullback of that isomorphism. Of that isomorphism from projection pullback. Was the projection 2 pullback of V nabla. Okay. So this is the descent data. shifts theoretically, and this gives rise to a rigid analytic connection. And then this gives to an algebraic connection. This is by Gaga, the rigid analytic Gaga. So that's the whole definition of this Frobenius pullback, local Frobenius pullback, together with this descent data. So, as I said, this is the kind of thing that, as you've probably seen in these crystalline papers, it goes on for 50 pages or so if you want to do the justification carefully. So. Right. So once you have this, nevertheless, once you've defined this Frobenius pullback, what we can do is define a Frobenius action on these drum torsors, the drum fundamental group and drum torsors. So what you get, therefore, is a phi action on P drum of X for, say, whenever the specialization of X is some k rational point in this situation. So right now, I guess I'm always assuming, well, this is just automatic because I know I'm assuming that all these things are f rational points of X. Yeah? So whenever you're in this situation, you get a phi action on this thing. How does the phi action work? Is this. So given any bundle with connection, well, you have its fiber at B, right? And its fiber at X. And we have to have a map from here to here, right? But the thing is, if you're given an element gamma inside here, then we'll have the fiber of this thing, of the pullback, Frobenius pullback of this at B, right? And there's a crystalline path from here to here because the fiber of this, remember at B will be the fiber of V at phi B, but these are lie inside the same tube, so there's a crystalline path from here to here. Yeah? And then same on this side, fiber of this at X is just the fiber of V at phi of X. Yeah? This is all happening locally, of course, for any local lift. Yeah? So there's a crystalline path here. So I won't denote all the indexing, but there's a P Chris here and there's a P Chris here. And our phi, our gamma gives us a path here for this pullback bundle, by definition. It gives us for every bundle such a thing, such a path from here to here. So then taking this composition gives us another path from here to here. This by definition is the phi applied to gamma at V. So let me say this again because this is slightly confusing. Of course, gamma will associate a normal isomorphism from here to here, right? But here's another isomorphism, this Frobenius twisted isomorphism, obtained by taking the isomorphism that gamma associates to this pullback bundle. That will give you this thing, right? But then composed with the crystalline path given by parallel transport, you get another isomorphism from here to here. That, by definition, going this way, is the isomorphism of phi gamma associated to the bundle B. Well, V nabla, strictly speaking. I should say. So that's the Frobenius action on P drum. And to make this explicit is quite hard. I mean, I don't know how to do it, in fact. Although, so let me write that again. So phi of gamma, by definition, is P Chris composed with gamma of phi pullback of V. Phi gamma as V nabla is P Chris composed with gamma at phi pullback of V nabla composed with phi C Chris inverse. So that's the definition. I forgot which direction I'm writing P Chris in, so depending on which direction you should put the inverse or here or here. But anyway, so to make this explicit is not at all easy, although I think I don't think it's intractable, but see, to make it explicit, what we have to do is compute everything that's going on here on this universal bundle. That's what it would mean to make this explicit. And I'll say something about that in a second. But the important part is the fact that still allowed us to deduce many things anyways, is that on the abelianization, U sub 1 dram. Yeah? Remember, for B equals X, this is just this Px is just the dram fundamental group, so we have an action on that. So this is just isomorphic to the dram homology, dual of dram homology of X over F. Right? Yeah. So this phi action is the usual one. Now, what do I mean by the usual one? See, this means we identified who's the crystalline pi 1 of Y. Okay. Dram homology. This is the dual of dram homology. Okay. And so there's a crystalline phi action, Frobenius action on that thing. And this is the usual thing. That's the theorem that one needs to say something about this situation. Yeah. And so I won't prove that. So that actually is not so difficult either, but as I said, it requires checking many compatibilities. So it's a bit tedious. Well, what's the consequence of that fact? So here's a very important consequence. It's this. So on U dram now, to U dram, we'll define a map, so-called Lang map of phi. Yeah, so Serge Wang finally makes an appearance. Yeah. This is the map that takes X to X phi X inverse. So this is sometimes referred to, the kernel of this map is sometimes referred to as the Lang torset for algebraic group in characteristic P. So here is p-adic thing, but so phi is a map of pro-algebraic groups from U dram to U dram, and then there's this map, which is the Lang map. So in abelian notation, it will be X minus phi X. Yeah? So this is surjective. So this also proof is by induction. So this to say, if you look at U dram, am I putting, yeah, sorry, I'm putting a superscript rather than subscript, sorry about that. And that's better since I also need the subscript for this quotient. So on U dram sub 1, yeah, it's clear. It's not clear, but this is a bunch of theorems. Yeah? So the point is that, remember, I just said that this is the same as H1 crystalline of Y. And the Frobenius is acting here. And this acts with weights the same as action on the p-adic Tate on the L-adic Tate module of the Jacobian. Yeah. So in particular, okay, so I'm a little bit sloppy here. In the compact case, the weights will be all minus 1. Even in the non-compact case, weights will be minus 2 and minus 1. Yeah. So there's no eigenvalue 1. So this is surjective. So phi here in this case, it really will be X minus phi X in the usual notation, and that's surjective. And similarly, on all these things, U dram n mod U dram n plus 1, which are quotients of tensor products of these things. So the weights are all negative. Yeah? So this thing will still be surjective. And then since all the U drams of n are successively expressed as torsors over a lower level for groups like this, you get surjectivity at every level. So I won't write down the details, but it's maybe inductively on it, using the weight of the Frobenius action on each of these tensor products. And here's the second corollary. P dram X has a unique phi invariant element. This is the so-called Frobenius invariant path, B to X. So the proof now is quite easy. So you say you just take anything you want inside there. Then phi of that will be gamma of u for some u inside u dram, because this is a torsor for u dram. Okay? But u, so u can be written as what? Phi, what did I write? Which direction did I write it? So some u naught, phi u naught inverse, right? Because of the surjectivity of the Lang map. So then this thing, phi gamma, becomes gamma of u naught, phi u naught inverse. So phi of gamma u naught equals gamma u naught. So there exists a Frobenius invariant path. And the uniqueness is also relatively clear. You see, if you have phi of gamma 1 equals gamma 1 and phi of gamma 2 equals gamma 2, then what you have, well, we know that gamma 2 is some gamma 1 times u for some u inside u dram. Again, because it's a torsor. But from here, we'll get phi of u equals u. Then by the inductive argument over there, by this weight thing, there is no choice. U has to be the identity. So that's the uniqueness. So there's a unique Frobenius invariant path inside all these U drams. And so what we can do now is the following. We use this to define iterated integrals. These are the Coleman integration. So, for example, so by the way, so what is this Frobenius invariant path? If you look at the way I defined this parallel transport, this action of Frobenius a moment ago, then in fact, remark, this is easy. If x and x prime are inside the same cube, then this path, well, I guess let me say this slightly more carefully. Suppose B and X are inside the same cube. Since I'm saying this with respect to a base point, of course, you could change the base point and give a discussion for any two points as well. But suppose they're inside, X is inside the same cube as B, then the Frobenius invariant path is the parallel transport. Discussed earlier. That's all it is. You take any base vector at B, and find the flat section with value that vector, and then take the value at X. That's the Frobenius invariant path. But the surprising thing here is that now we can extend that to to points on two different tubes. This is some kind of a mysterious thing, that we can take horizontal section on one tube, and there's a canonical way to transport it over to horizontal section on another tube. So Coleman gave a description of this in some very explicit way, which can be used for computations. And I don't know how to do it, because I still have been too lazy to actually look up how it's really done in computation. But there's this abstract formalism that shows you that it exists anyways. That all these antiderivatives on one tube can be made canonically compatible with the antiderivatives on another tube in this manner. So in fact, suppose that you want to define, say for example, suppose alpha is a differential form, and you want to define integral from b to x of alpha. This is Coleman integration. And as I said, Coleman has this very explicit description of this procedure, but the abstract description is this. Yeah? What we do is we write down the connection OX squared, yeah, together with d minus 0 alpha 0 0. Yeah? By the way, so this, of course, by the definition of this way of this element is compatible with maps between connections. That's important here. So I guess I didn't give this element a name. I'll call it P Chris of X. Yeah? It's an element inside here. Yeah? So here's our vector bundle. Yeah? Then P Chris of X is supposed to give us an isomorphism from here to here. The fiber at B to the fiber at X. Right? Which, since this is a trivial bundle, this is just going to be f squared. Both will be just f squared. Okay. And because of the compatibility between maps of connections, this has to take the form 1, 0, 1. This will, in other words, it has to be the identity map on the trivial quotient and the trivial subbundle. Yeah. And then there will be something over here. It has to take this form. Yeah. And this, by definition, is the integral from b to x of alpha. Whatever occurs there. That's the Coleman integration by definition, which locally is the right thing. It's the intuitive thing that you get by taking antiderivatives, taking formal antiderivatives. But this is a way to integrate from one cube to another even. If you want to do iterated integrals, you do something similar. You just take, say, suppose you want to do iterated integral alpha beta. I may get the order wrong, don't hold me to this order, but just consider OX cubed together with the connections 0, 0, 0, alpha 0, 0, 0, beta 0. And then again you get a map from f cubed, namely the fiber of OX cubed at B, and the crystalline path will take us over to OX cubed with X, F cubed. And this has to take the form 1, 0, 0, star 1, 0, star 1. It has to take this form. And this will be the integral from b to x of alpha. This will be the integral from b to x of beta. And this thing, by definition, is the integral from b to x of alpha beta. Which, again, if you were locally, it is this naive antiderivative process that we would actually be doing. So this is this procedure. So how does one use this? No. Finally. So I wanted to, in this lecture, to at least tell you how one sets up the basic diagram that applies to diophantine geometry. But as I said, how one uses that diagram, maybe I've spoken enough about. So there's an idea of the technique behind setting up the diagram. But unfortunately, there's one ingredient I still don't have time to do, which is that all these p drums, so these are u drum torsors with two things. One is the compatible phi action. Phi action I've just explained, and it should be completely obvious from the definition. Well, again, you have to write down a few diagrams, but the phi action is compatible with the composition of paths. That's very clear from the way it's written down, the naturality of the action. But the other thing is that there's a compatible Hodge filtration. So this as well, unfortunately, there isn't a completely accessible treatment. The full discussion. Of course, this Hodge filtration initially only defined over C, and then you have to descend it to this other field and show that it all makes sense algebraically. So this is the other thing which, at least for curves, I'll write down in a completely accessible form in the write-up of these lectures, how one defines this Hodge filtration. But at least I'll remark. So this is a pro-algebraic group. This is a pro-algebraic variety. So what this means is that there's a filtration by subgroups and subtorsors. So there will be F naught of U dram will be contained inside F minus 1 of U dram, contained in F minus 2 U dram, and so on. So these will be subgroups of U dram, not normal subgroups in general, but there will be same thing for these torsors. By sub-varieties, with the property that F naught of P dram is F naught of U dram torsor. That's the key thing. So that's what happens with all of these objects. So these kind of torsors for U dram is compatible for Frobenius and Hodge filtration. So the point is these are classified by U dram mod F naught of U dram. And the reason is as follows. What you do is, for example, so this is true for any such torsor, but the point is that if you have such a thing, inside here you have F naught of P dram, right? And so this torsor is a torsor for a unipotent group over a field, QP, over the field QP, or actually, sorry, I was a little bit sloppy. I realized, amid all the other sloppiness, I included one more. So at this point, in fact, let me assume that F equals QP. Otherwise, in this whole discussion, I'm actually working not, because we started with an algebraic group over F, but what the discussion actually concerns the restriction of scalars from F to QP. And we don't want to go into all those things, so we'll just assume that F equals QP at this point. So this is a QP algebraic, this is a torsor for the QP algebraic group F naught of U dram. And torsors for unipotent groups over local fields are all trivial anyways. They're not canonically trivial, but there exists an element in here. So what we do is we choose inside here P dram. Inside here. And in any case, there's the other element P crest in here that we discussed a moment ago, the Frobenius invariant element. And then the difference between the two things, so let me say this slightly carefully. P dram will be P crest times an element U, where U is inside U dram, right? Because it's a torsor. And this U dram, if we choose a different element of F naught of P dram, because this is an F naught of U dram torsor, this will change by an element of F naught of U dram. So in fact, the class of this U inside U dram, or F naught of U dram, this is well defined, just depending on this torsor. So these torsors with compatible Frobenius and Hodge filtration are classified by this homogeneous space for U dram. So I'll summarize what we have so far. Putting all this together. What we have is the following. We have X, and you might have the S integral points of S, which are the rational points if it's compact. And then we have the integral point of the completion, the p-adic integral point for some v-adic. And we have the map from here to here. And then we have a map from here to h1 of gt with coefficients in un. And we have a map from here to here of h1 of gv, the local Galois group, with coefficients in un for any n. And there's a localization map from here to here. And then there's u duram mod f naught, and there's a map from here to here. So, and we know what these maps are. These maps in the vertical directions all send something x to this p, this torsor, this étale torsor. I guess I don't remember if I put the superscript there, from b to x, torsor of paths from b to x. And this map is the one that sends x to p duram of x that we just discussed. And the thing is, inside here there's a h1 sub f of gv of un, whose inverse image here will just denote by h1 sub f of g of un, the global object, in such a way that this thing mapped here, actually isomorphically, although it's not so important to know the fact that that thing is an isomorphism all of the time. And the point is that this local object thereby acquires a very explicit description using this u duram. So the cohomological object, but now we still need to retain this description because this is the thing that connects it to global objects. But then when we localize at V, it has this concrete description in terms of an algebraic group whose coordinates we can describe and so on. So let me conclude with, sorry, I'm going over time, but if you, maybe it won't be so bad if I just go over by 10 minutes and describe this h1 sub f, because
unless you want to give another lecture on Monday.
Maybe it's best not to try people's patience. Maybe it'll be better just to take 10 minutes here and then leave further things to private discussions. Yeah. Let me just describe the h1 sub f because it's actually a fairly concrete object, even though I may have made it look complicated in various discussions. So first of all, the thing I'll take as a black box is B crys. This is Fontaine's ring of crystalline period. Okay. So I have a feeling I did the canonical thing that one does on these circumstances. Spend a lot of time doing the easy things and now rushing over the difficult parts. Anyways. Now if we take this U and take the B crys points of that thing, this has an action, GV action. I guess I forgot to say this. By this I mean, of course, F V var over S. This has a continuous GV action. And there are various ways to see it. One way is the way I think I described it in my paper. This just can be seen as the coordinate ring with homomorphisms from the coordinate ring of UN to B crys, so that it acts on the target and on the source. But the other way to see it is, remember, Galois, as a Galois model, this is just Ln tensor B crys. This can be identified with the Lie algebra. So this is just, this has the Galois model structure and this has the Galois model structure, so it just acts here. So here, of course, there's also all these things like the cocycles with coefficients, continuous cocycles with coefficients in B crys, and then mod out by U and B crys, the action. And we did the same kind of thing here. So we can discuss H1 of GV with coefficients in this object in B crys, in the same manner as we were doing it with algebras. So the difference actually from the previous discussion is when we were taking arbitrary QP algebras in the abstract way, those QP algebras had trivial action. This B crys itself has an action, so it's somewhat different from that. And we have this map from H1 GV with coefficients in UN to H1 GV with coefficients in UN B Chris, simply because QP maps to B Chris. And H1 sub F is the kernel of that. Kernel of the map. So in other words, these are things that are represented by cocycles that trivialize in U and B Chris. Now that's a slightly mysterious looking condition, and it can be phrased in many other ways. For example, if you view it as a torsor, then it's equivalent to the condition that the coordinate ring of the torsor has a crystalline action, a crystalline Galois action, and all those things. But in fact, I'll just use this definition to explain to you how this map is defined. This map is, this is Fontaine's functor, but if you just take the abstract description via Fontaine's machinery, it's slightly hard to imagine how it could be computed. But instead, I'll give an explicit description just using this definition, which is actually, I think, the way one would eventually compute this map. But at least an ingredient of the kind of description that makes it more amenable to computation. So here's what one does. So if you look at this space, H1 of GV, let's look at it at the level of cochains, U and B, right? There's a map from U and B Chris to this, simply sending everything to the trivial cochain. Let me just do the direction slightly carefully. Because, yeah, I'm going to. This is the map that sends U to, well, C sub U, whose value on sigma, according to the convention I had before, was U sigma U inverse. I'm going to do it this way, actually. I think I wrote it the other way around, but it doesn't matter because by replacing U by U inverse, we just get the same. These are all the trivial cochains are all the same, trivial cocycles. So there's that map on the one hand. On the other hand, we have the map from GV of UN to this thing via inclusion. And the crystalline cocycles are the ones whose image here lies inside the image of this map, right? That's the definition. So let's form the fiber product. This. So what we'll get is H1 Z1 sub F GV UN subset here is mapped onto by U and B Chris fiber product over Z1 GV U and B Chris, and then here is Z1 GV UN. Yeah, sorry, this is all of notation, but there's this fiber product of this space, and that surjects onto this by definition of this space. Okay, now let's just examine that map for a second. Here's the point. Now look at the map from the points of UN to the cochains. Well, suppose, actually, maybe I'll give a name to that map for a second. I'll call this map F or something. Too many things are called F. Let me call it H. So, first of all, let's suppose that H of U1 equals H of U2. What happens then? Let's examine the fibers of that map. Well, see, what this means is that U1 sigma U1 inverse equals U2 sigma U2 inverse. Right? But then that means, I guess, the U2 inverse U1 equals sigma U2 inverse U1, right? So in other words, U2 inverse U1 is inside the Galois fixed part of UN Durand B Chris. That's what it would mean. So we can write, I guess, U1 as U2 times U2 inverse U1. You know, this element where this is GV fixed. So the point here is that the fibers of the map of H are torsors for this thing UN drum B Chris GV. Actually, the converse is also easy. That if you take U2 and modify it by a GV invariant element, you get the same co-cycle associated to it. So in fact, fibers are exactly torsors for this. But what is this? This actually, sorry, this isn't drum at the moment. This, why did I, yeah, sorry, this should have been, so far this is the étale UN, yeah, sorry, this wasn't, so far, I anticipated what I was going to say. This was just the étale UN with the Galois action so far. But if you take this, the theorem is that this is actually UN drum. This is the non-abelian periodic Hodge theory. This is exactly this. Now you have to say this, the thing is, one has to say, so for example, for n equals 1, this is simply the fact that that étale cohomology is under Fontaine's functor that tensors everything with B Chris and takes the G invariant, goes to drum cohomology, for example. This is just a non-abelian version of this. So that's the statement. So what we have is, what have we done? We've associated to each crystalline co-cycle, U drum torsor, namely, start with this element and just look at it. So if you take an element in here, so H inverse U, H inverse of C is a U drum torsor. And that's the map from here to here. That takes C to H inverse of C. Now, what I didn't discuss is how you get the Frobenius section and stuff. So it is a torsor, but where does one get the Frobenius section and the Hodge filtration? And this is the usual thing in Fontaine's theory, that this B Chris has the Frobenius section and Hodge filtration, which induces the one that you want on this U drum. But if we just, in fact, here it's convenient to look at it this way, because this now will have a Frobenius section and Hodge filtration, and that just induces the one here. And the point is, of course, you want all these things to be compatible. For example, to check that the Frobenius section is compatible with the group structure, well, remember this UN is the same as Ln with this twisted group action, twisted group law, composition law. But all you need to check is that the Frobenius section is compatible here with the Lie algebra bracket, the Lie bracket. Because then the group law is given by using the Lie bracket at addition many times, right? So it just needs to be linear and compatible with the Lie bracket. But that follows because, well, I didn't say it, but the way the Frobenius acts, well, okay. Let me restate. The way here, it's completely obvious actually, because I was thinking about something else, because it's just defined on coefficients. So the fact that it's compatible with the Lie bracket and linear in Ln is completely obvious. So in fact, it's compatible with the group structure. And you have to say a little bit about the Hodge filtration as well. But the torsor you get here eventually carries a Frobenius action and a Hodge filtration, and that's the map from here to here. So this is the diagram that I've discussed in many lectures so far, about which I guess I've never actually in a lecture discussed the details. Well, it's not so hard, but I didn't do such a good job of explaining it. But anyway, so I think I've said enough now for the foreseeable future.